morning, everyone. Please welcome Jeff Kopsick from Madison University and his presentation on exploration of 3D printed environments for sea elegans.
Well, good morning, everyone. I am Jeff Kopsick. So first, I guess we'll address what is sea elegans. Well, sea elegans are about a millimeter long roundworms, i.e. nematodes. And they've been used in a wide array of STEM fields to study such things as trying to understand diseases such as like Crohn's disease that use like certain sea elegant cultures, all the way to what I'm doing, which is looking to understand locomotion. So they typically have about a 3-day lifespan, around 3 days, based off the standard protocol, which it basically states that sea elegans need to be incubated at about 20 degrees Celsius when they're being grown, and they feed off of a bacteria called Kopsick, and they can survive typically up to about 3 weeks. But why I'm interested, and as I've said before, I'm trying to understand locomotion. And typically, sea elegans will exhibit either crawling motion or a swimming motion. And that crawling motion typically takes place on the places, or these agar plates where they're being grown, and within a droplet of solution. And a typical solution would be that of an M9, or a combination of the carboxymethylcellulose in this M9. So what I'm interested, though, in is that how will 3D printed environments affect swimming motions, and if it's even able to be done. And first I look into different geometries of these environments, and we can hopefully see if that will help us out at all. So, as I was saying earlier, there's different crawling motions and a swimming motion pattern. So the first pattern that we see is it crawling on an agar plate, and it looks like it's exhibiting a 1.5 sine wave type of motion. And then we flip to looking at it in a swimming pattern, or swimming in the M9 solution, and we see that it's looking like a 1/2 sine wave. So definitely there's a qualitative difference between the movement types. And how we record these videos is done on the microscope that we have in our lab that one of the faculty members in the department, Leanne, has cleverly named the Worminator 2000. So typically I will go in and I'll get a worm that I'm going to try to put into a plate. I'll typically place this on a glass slide. And I'll place it in the solution, and I'll put it under that microscope on the stationary platform. And basically how I'm able to track movement is by use of these linear actuators. So basically the linear actuators move the stage, and I can do that manually through the computer. But what's most important, though, in taking these videos is the camera, and how if there's a top-down light source, or a top-down light source, or a bottom-up light source. And typically, when I'm taking a crawling video on the agar plate, we'll be using a top-down light source, and this is a non-strobing light source. And then with I'll use the bottom-up light, bottom-up lighting for when I'm trying to look at the swimming patterns, because sometimes you'll see blurring that will occur during the videos, and we can correct for this with a non-strobing, or with a strobing light source rather. Anyways, moving into actually creating these 3D environments. Well, I first started off in my 6D lab course that was taught by Dr. Tallman last year, and I started creating these box frameworks for the worm. And I wanted to see whether or not, these could even be created. And I used, at the time, it was the only 3D printer that we had in the math department, and that was the MakerBot Replicator 2. What I noticed, though, when I was trying to print out these different designs, was that I was literally testing the limits of this printer. The bases, which you will see, or you can't really see them from this view, but as I made the bases thinner and thinner, the printer actually wouldn't even be able to recognize it. It would get mad at me. It's like, no, I don't want to even do that. So I was only able to get down to about a base with 0.3 millimeters And I saw that putting that under the microscope, I wasn't able to identify the outline of the worm, which is really important in trying to get the data from movement. So where did that lead me to? Well, we were very fortunate to be able to get a second 3D printer in the lab, and that came in about June of this year, and I was able to get down to a base of about 0.2 millimeters. And with this design, which actually printed off these boxes even nicer, it still wasn't able to see the edges of the nematode, even at a 0.2 millimeter thin base. So I looked into acetone. So what acetone really does when it's applied to this ABS plastic that the printer is extruding, what will happen is you'll print off your design and it'll be really rough, which you can see from here. So this is not my design, but this looks like a squirrel or something. So with that rough design, this was placed in an acetone vapor bath, and when it was treated with that, you can see that it's much more smooth and glossy. So I thought to myself, would I be able to even do this for a design as small as mine? And what I did see is that it did make what was called, the webbing that occurs between sometimes when it's the plastic's extruding. It got rid of this webbing, and it made the design nicer, but you still could not see those edges. So I next looked into using a glass slide. Now, glass slide I would typically use just for that droplet of the solution, and I didn't have any problems with viewing the worm. So when we went to this glass slide, it turns out just printing off on the glass slide by itself, just that smooth surface, the printer actually cannot have it stick down. So I looked into using an acetone ABS glue, which basically has the ABS plastic being dissolved in this acetone, and I applied this glue. I smoothed it out by using two different glass slides, and then rubbed the edges against each other, and was able to create what I have down there, which looks like this whole entire region where you have that acetone-based glue, and I was able to print it off. However, there was still, some sort of webbing that was going on, and I wanted to be able to make sure that I would actually be able to see those edges. So once I applied an acetone vapor bath, I was able to create what I have here on this slide. And basically, when you are viewing the worm just by itself, not in this 3D environment, you would have to use a spacer in order to keep the air pressure from not getting to the droplet. So what I did was I created these spacers with a 3D printer as well, incorporated that into my design, and I put it in a slide holder to make it more convenient to bring over from the part of our lab where I am actually picking these worms to be studied, and then over to the microscope that you had seen earlier. So that slide holder is really nice because I can just place it under the microscope and be able to find the worm very quickly. And thus I was able to actually get a really nice image of the grayscale image of this nematode where you can clearly see those edges. So now that I actually have an image of the worm, how will I be able to take an actual video? So I was able to take this raw video of the worm by actually having the microscope set at recording at a frame rate of 10 frames per second, which allowed for none of the scenes to be deleted, which is really important when trying to incorporate data, because if you have deleted scenes, you're not accounting for all that, the movement pattern. So how was I able to actually, be able to quantify what the movement pattern was? So I ended up using MATLAB, and as somebody who's very new to the whole coding experience, I had to extrapolate. And basically I took, at first, one frame out of the entire video. So I started off with one frame and the original grayscale, which was an original grayscale image, which is really nice because that's what our microscope records with. So I move from this grayscale image and I say, what do I want in my segmented outline? Well, I want to be able to look for a change in background from what is the worm and what is not the worm. And I can modify that into a binary image, which is really important when getting the outlines, one of the only ways you can really do it with this worm. And I modified this by use of a default Sobel edge detection method and what's called a fudge factor function. And I was able to receive this nice binary image where you can see the outline of this worm. However, what you'll notice is it just looks like a bunch of dots, and that will make up this rough outline of the worm. So how do I make it smooth? Well, I dilate some of the edges, or I dilate all the dots within the particular image, and I was able to connect these dots with this dilation function, and I was able to create this rough outline. However, it would be really nice to be able to actually fill the space between the worms.